So, welcome friends to this session of our discussion. Today we will discuss the discrete time optimal control system, which we are discussing from the previous class. So, in the previous class we have seen that variational calculus can also be applied to the discrete system. We are minimizing a functional which is given as the v xk plus 1 k plus 1. Variation at the optimal point is x star k plus delta k, and at xk plus 1 is x star k plus 1 delta k plus 1. So, we define j star and j star at the optimal point and j star at the variation point x star k delta xk. We find out the increment, and from the increment we define our first variation as delta j. In the first variation we got the two terms delta xk and delta xk plus 1. So, this second term we convert in the form of the delta xk. In this conversion we got the first term as delta v x star k minus 1, which is the coefficient of delta xk, plus the boundary condition which is given as delta v x star k minus 1 x star k k minus 1 delta xk at the point k equal to k0 and k equal to kf. So, k equal to k0 is my initial condition and k equal to kf is my final condition. So, in normal case we are given with the initial condition. So, delta xk0 will be 0 and we will left with the boundary condition as delta v x star k minus 1 x star k k minus 1 by delta xk at the point k equal to kf, and this must be equal to 0. So, this is my terminal condition and this gives me the EL equation in the discrete form. So, this we have done in the previous class. So, today we will see in that discussion we have not considered the terminal cost. So, if you will consider the terminal cost also with my performance index j. So, my j is now s x of kf where kf is the terminal point. So, this define my terminal cost and this is my summation cost. Again in the similar manner we consider the variation at the optimal point of x star k plus 1 as x star k delta xk for xk plus 1, this is x star k plus 1 plus delta x of k plus 1. Our approach is similar. Again we define j star in terms of the terminal cost and j at the point x star kf plus delta x of kf at the variational point. So, after defining j star and j, my next step is to find out the increment. So, next we will find out what is the increment and how we define the increment. Delta j as j minus j star. As we know, so we can write delta j as j will have my first term. So, I am subtracting j star from j. So, this is s x star kf plus delta kf minus this. So, I will write these two terms together s of x of kf plus delta x of kf minus s of x of kf. So, this is the first two term I am subtracting j minus j star, and second will be the summation subtraction plus this is from k0 to kf minus 1 v so we can say put the star here because this is at the optimal point, this is at the variation point, x star k plus delta x of k x star k plus 1 plus delta x k plus 1 and k. So, this is my summation term of the j and minus v x star of k x star of k plus 1 and k. So, if you will see my summation term, this is similar as we have considered in the previous case. So, once we will expand this with Taylor series, expand using the Taylor series. So, I will get from the terminal cost S x star of kf plus del S by delta x of kf delta x of kf minus plus higher order term minus s of x star of kf and plus this summation term. So, this summation expansion is same as we have considered in the previous case, same as considered previously. So, this we will take up same as we have done before. This s will cancelled out, this higher order term we neglect. So, what actually we will left? We will left say, if you will see from the summation, I will get the first this summation term same as we have considered in the previous case, plus the boundary condition for k0 to kf, plus this is additional term which will appear in the first variation. Now, I can, as my initial condition is given or it is already defined k equal to k0 and x of k0. So, delta x of k0 will be 0. So, this is left only with the kf term. So, this term will left with the kf. So, what we are saying, del v x of k minus 1 x star of k minus 1 delta x of k. So, we are considering this term with delta xk and we are evaluating this as k equal to k0 and k equal to kf, plus we are getting del s kf by delta x of kf into delta x of delta x of kf. So, in this term at k equal to k0, my delta x k0 is 0 as k0 and x of k0 is specified. So, x of k0 will be 0. So, I am left only with the x of kf. So, delta v, I can write this as x of k minus 1 star, we are placing here x star k minus 1 by delta x of k. So, this is evaluated only at k equal to kf point, plus this delta s So, now at k equal to kf I am evaluating this, I am also evaluating at k equal to kf. So, I can club these two to get my boundary condition as del v x star k minus 1 x star k minus 1 delta x k plus delta s by delta x, and the whole we are evaluating at k equal to kf point. So, with this again we have the EL equation in the discrete form, plus my boundary condition will be given by as this second equation. So, even with the terminal cost, my additional term which is appearing, that is del s by del x, which is given. Now, this concept with the terminal cost now we can apply to our optimal control problem. So, we take its application to a linear time varying system. So, we are considering linear time varying system. So, this linear time varying system we can consider as x of k plus 1 equal to a k x k plus b k u k. It is a very standard equation, and we are given with the initial condition as x k equal to k 0 given as the x of k 0, and the performance index of the plant we can take as j equal to j x of k 0 u of k 0 k 0, because we evaluate performance index as we have seen before at the initial point, this directly give. This is equal to the terminal cost, which is defined as half of x prime kf, f of kf, x of kf plus half of now summation of x prime qx plus u prime ru at the kth instant, where k is varying from 0 to kf minus 1. So, for this linear time varying discrete system, my objective is to find the optimal u which will minimize the performance index given as j. So, what is our approach? First we will define a augmented cost functional. So, the solution of this problem we will start from our Lagrangian approach, and then we will convert the Lagrangian into the Hamiltonian, and then find out the final equations which we will have. So, what is my Lagrangian? Lagrangian we define as V plus lambda prime G, where G we will take as 0. So, by this we are writing first the augmented cost functional, which is include the terminal cost plus half of. So, this arm augmented x prime qx plus u prime ru plus lambda k plus 1 akxk plus bkuk minus x of k plus 1. So, this term represent nothing but my g. So, if g equal to 0, so this means my this equation akxk plus bkuk minus x k plus 1, this giving me the 0. So, if we will see, my augmented cos functional is same as the cos functional we have considered before, given as j. So, the minimization of the j is same as the minimization of the j. In this, here we are defining my Lagrangian as half of x prime qx plus half of u prime ru plus lambda prime k plus 1 akxk plus bkuk minus x of k plus 1. So, this is defining my Lagrangian. Now, in this the question may be what should be my Lagrangian function, this lambda prime. Lambda prime we can take it as lambda prime k or lambda prime k plus 1. So, we have taken intentionally this as lambda prime k plus 1. The reason will be clear later on, because this made our further calculation or the further expression to simplify. We are considering lambda as a function of k plus 1 in place of the k. So, if Lagrangian is defined, where Lagrangian is a function of xk, uk and lambda k plus 1. So, by this we can directly write our Euler equation as we have derived before. We can follow the same approach as I can define my Lagrangian at x point. I can define the optimal Lagrangian, Lagrangian at the variational point, and then find out the increment. So, this approach is similar as we have done before. We have find out the first variation as del v by del xk, where v is a function of x star k plus 1 and k. So, the two another variables we are adding into this, which are as my uk and lambda k plus 1. So, my Lagrangian equation I can write simply as del L by del xk, del L by del uk, del L by del lambda prime k. So, these three will be my EL equations with respect to my state, my control, and the third is my nothing but the co-state which we will have, and my boundary condition will be del L k plus 1, x of k plus 1, u of k plus 1. So, del L is a function of this, because we have considered my final condition as del v x star k plus 1, x star k at k minus 1 point. So, naturally once I will write my final boundary condition, that will be del L x of k plus 1, u of k plus 1 as the lambda k plus 1. So, here it is coming in the lambda k plus del s, which is nothing but giving me the terminal cost delta x of k equal to 0, where s xkf kf, if I will evaluate this point, is nothing but half of x prime kf f of kf x of kf. So, in Lagrangian form I got these three EL equations and the final boundary condition given as this. So, this optimal control problem can directly be solved using the Lagrangian approach, or further we can simplify this using the Hamiltonian. So, we define our Hamiltonian H. What is H? Which compared to L? Plus lambda prime, here we will take in place of the G F, where we are considering x dot equal to F. So, only we will consider F here in place of the F minus x dot is G. So, for this case my G is F minus x. So, this is the difference between Lagrangian and the Hamiltonian. So, here we take v dot plus lambda prime f, and what is my v and lambda prime if we will see. So, from my performance index, my first two term half of x prime q x plus half of u prime r u, this is my v plus lambda prime k plus 1, and this is my f a k x k plus b k u k. So, this define my Hamiltonian, and in terms of Lagrangian if I will write this. So, what was my Lagrangian here? We have considered the Lagrangian as half of x prime q x, half of u prime r u. Now, lambda prime k plus 1 a k x k plus b k u k up to this. This is my h minus lambda prime k plus 1 x of k plus 1 is subtracted. So, I am writing my L in terms of the h minus lambda prime k plus 1 x star of k plus 1. So, this is giving me Lagrangian. Now, if this Lagrangian in terms of the Hamiltonian I will use with these equations. So, I can get all the EL equation in terms of my Hamiltonian. So, I am writing my L is a function of x k, u k, x k plus 1, lambda k plus 1, and this is equal to my h, which is also the function of x k, u k and lambda k plus 1. So, h is not a function of x of k plus 1, this is the function of x k, u k, lambda k plus 1 and minus we have lambda prime k plus 1 x of k plus 1. So, we will have this value because lambda x of k plus 1 is separated out from the h, as we can see from this. No x k plus 1 term appear in the Hamiltonian. So, now this L in terms of the h we can use in these equations. So, my first equation is del L by del x star of k. So, del L so what you will get by this first term, where L we are taking this with x of k. If we will differentiate this with respect to x of k, I have only term with the h. So, this I can write simply as del h by del x of k, while this term will give me the 0. My second term is del L x star k minus 1. So, if I will write L as x of k minus 1, u of k minus 1, this will be x of k lambda k, and similarly here will be the h x of k minus 1, u of k minus 1, lambda k minus lambda prime k x k, and this I have to differentiate with respect to x k. So, naturally only x k term will appear. So, with this second term we are getting only as lambda k. So, this term I have to differentiate with respect to xk. So, this will give me 0 and this give me only lambda k. So, this is minus lambda k and this will be 0. So, what I will get? Lambda k as del h, which will be the function of my xk, uk, lambda k plus 1 by delta xk, and this is nothing but my this equation I am getting, lambda k equal to del h function of xk, uk, lambda k. So, this nothing but giving me the co-state equation. So, this will be my co-state equation. Next we have to take del L by del of, let's uk. This means the second equation we are taking del L by del uk, second EL equation. I am placing this Lagrangian in terms of the Hamiltonian. So, with respect to k, k plus 1 uk, I have to differentiate this. So, this will give me, so first I am differentiating the first equation, which is L of xk, uk, xk plus 1, lambda k plus 1. H is a function of u, so naturally I will get del h x of k, u of k, lambda k plus 1 by delta u of k. My next term, then I have to differentiate this L with respect to uk, and here if you will see, h is not a function of uk, this is also not a function of uk. So, this term will be give me 0. So, if I will write this equation, so this is nothing but del h by del uk plus 0 equal to 0. So, this means this must be equal to 0. So, my this equation will be nothing but del h with xk, uk, lambda k plus 1 by delta u of k, that will be 0. So, by this I am getting my this equation del h by del u with xk, uk, lambda k plus 1 equal to 0. Then I have my third equation as del L by lambda k, del L k minus 1 by lambda k. So, this means I have to differentiate these two with respect to lambda k. So, from the first term, this is del L, this I am saying first, let us say this I am saying second, del L by del lambda k, what we will get? So, we having del L by, so this term I have to differentiate with respect to lambda k, and this whole term is independent of the lambda k, sorry, this will give me 0, while the second term, what actually I will get? X of k plus 1, u of k plus 1. So, this is h is a function of lambda k, as well as my second term is also the function of lambda k. So, second term will give me, if for the second term I am taking, so this is x of k minus 1, u of k minus 1, lambda k by del of lambda k again. So, if I will differentiate this, what I will get? Del h, which is x of k minus 1 u of k minus 1, but function of lambda k. So, this means h I can differentiate with respect to lambda k, and this lambda prime k x k, if I will differentiate this with respect to lambda k, this will give me nothing but x of k. And by adding these two terms, so this is the first term which is written here, this is the second term. By addition equal to 0 is giving me the EL equation. So, this give me nothing but del h x of k minus 1 u of k minus 1 lambda of k differentiated with respect to lambda of k minus x of k equal to 0. So, x of k equal to this. So, I will get my, from the third equation I will get my equation as x star k delta h x star k minus 1 u star k minus 1 lambda k by lambda k. So, I got, so this is my control in terms of the Hamiltonian, del h by del u equal to 0, x star k del h by del lambda k, x star k plus 1 u star k plus 1, in this we have to mind this. This is my state equation, and lambda star k plus 1 as x star k u star k lambda k plus 1, this is my co-state equation. So, this, that is why we have taken as the lambda k plus 1 to get this equation in lambda k. So, what actually we are doing in the next, now this x star k I am getting, say these two terms are in terms of the x k u k lambda k plus 1, this is also in terms of the x k u k lambda k plus 1, except this middle term which is x star k minus 1 u star k minus 1 lambda star k minus 1 lambda, sorry, differentiated with respect to lambda k. So, this we can write as, so I can write this equation as x star k plus 1, so that my this term can be converted into h of k. So, this is delta h. Now, this will be the function of x k u k, here lambda k plus 1. So, my h is similar in all the three equations, control delta x of, because we have made the k plus 1. So, this is delta with respect to I am differentiating lambda k plus 1. So, what is the advantage of having this? Because now I can define my h x k u k lambda k plus 1. How we are defining this? This is my v, which is nothing but half of x prime k q k x k plus half of u prime k r k u k plus lambda prime k plus 1 a k x k plus b k u k. So, now directly now I can have the differential of this H with respect to xk, with respect to lambda prime k plus 1 and with respect to uk. So, my all equations with the given Hamiltonian as H, I can directly have del H by del u equal to 0, I can have del H by del x equal to 0 to get my co-state, and del H by del lambda prime k plus 1, because this is defined as the lambda k plus 1, direct differential with this. So, that is why initially we have taken, in place of the lambda k, we have taken the lambda k plus 1. So, my h k, if I can define the Hamiltonian, directly I can write my equations. So, I stop my discussion here for this session, and further how we will utilize these equations to develop the difference Riccati equation, that we will discuss in the next class. Thank you very much.